All right, now that you know how to write the equation of a line parametrically, we're going to learn how to write the equation of a tangent line to a curve parametrically. Okay, so if we're given some sort of parametric curve and we want to know what the tangent line is at a point on that curve, then what we want is a straight line through that point with the same velocity in the x and y directions as the particle moving along the parametric curve that we're given. So that's a lot of words. Let's just dive in and do a problem here. It'll make more sense. So we're given the parametric equations for a curve. X equals t cubed and y equals 2t. All right. And we want to find the tangent line at the point 2 comma 1 in parametric form. All right. So, all right. So we have the point. So that's our x0, y0. And so what we need is the velocity in the x and y directions at that point. And we can find that easy enough. Dx dt, we take the derivative of x with respect to t, we get 3t squared. All right, and dy dt is equal to derivative of 2t is just 2. All right, so that gives us velocity in terms of t, but we don't have t, we have a point. So we've got to figure out, okay, what point in time is this one, are we at this, is this particle moving along this curve, is it at the point 1 comma 2? So we just got to figure that out. So we want x equals 1, right? X equals 1, and so that'll happen when t cubed is equal to 1. So that just tells us t equals 1. And that's really all we need. And we can verify, though, that, we were looking for the point when y equals 2, right? And that's got to happen when 2t is equal to 2, which also happens at t equals 1. So that verifies that it works. That is a point on the curve, right? At t equals 1, we're at this point. But we need that t value because otherwise, we need to be able to we need to be able to evaluate the velocity at that point, right? So we had to plug in t equals 1. So at t equals 1, the velocity, Vx, right? So this is really Vx, and is equal to, let's plug in 1 and we get 3. And the velocity in the y direction, right? That's this, Vy. And that's always 2, no matter what t is. Okay, so there's our velocity in the x and y directions. So what we want is a line that passes through the point 1, 2, and travels at this rate, right? So we can just write this as, okay, we're going to start at 1 for the x value. We're going to start at 1 and we're going to travel at a rate of 3 for every time period. So we have a parametric equation for x of 1 plus 3t. And then for y, we're going to start at 2, right? And traveling at a rate of 2 units for every unit of time. Okay? So these are parametric equations for a tangent line to the parametric curve at the point 1 comma 2, right? Because they'll pass through the point 1 comma 2 with the same velocity at that point as the original parametric curve. Okay? All right, so let's take a look at part B here. We were asked to find the tangent line at 1 comma 2 in Cartesian form. Now I'm actually going to do this 2 different ways. One way is just to take those parametric equations for the line that we just found in part A and eliminate a parameter, right? So we can do it. Let me pause. Okay, so I just wrote down what what I'm going to do. I'm going to do 2 different ways. And the first way is just by taking the parametric form of the line I just found eliminating the parameter. So I can solve for t in the x equation. So I'm going to get t is equal to x minus 1 divided by 3. And then I'll just substitute that into the equation for y, and I get 2 plus 2 times x minus 1 over 3. And then I'll simplify that, and I'll get 2 plus 2/3 x minus 2/3, which becomes y equals 2/3 x plus 4/3. Okay, so there is the equation for the tangent line in Cartesian form, and I did it just using the parametric tangent line that I just found. Now we can also just do this the old-fashioned way, the way you already know how to do. If we take the original equation, the original parametric curve, and eliminate the parameter on that. So if I rearrange the x equation, I get t is equal to x to the 1/3, right? And then I can substitute into the equation for y, and I'll get y is equal to 2 times x to the 1/3. Okay, so now instead of a parametric curve, I have the Cartesian equation for that curve, and then I can just find the slope at any given point. So let's find dy dx, right? I'm going to get 2/3. I'm going to differentiate the x to the 1/3, so that becomes 2/3. Let's see, x to the minus 2/3, right? I'm just going to drop the 1/3, take it times 2, and then subtract 1 from the exponent. Okay, so that's the slope. So then at x equal 1, the slope, which is dy dx at 1, is just going to be 2/3. Okay, which is good. That's the slope I got down here in the other one. All right, and then we're just going to use the point slope form of the line. I'm going to use the point 1, 2, and I'm going to say y minus 2 is equal to the slope, whoops, which is not 3. Let me erase that. So it's 2/3 x minus the x value, which is 1. And then I rearranged that, and I'll get, now I'm going to take some shortcuts here because I'm running out of room, 2/3 x plus 4/3, right? So I get the same equation either way. Notice these are the same equation, right? Here I did it the old-fashioned way. On the right-hand side here, I did it the old-fashioned way, just by differentiating the Cartesian form of the curve, and in the other one, I just eliminated the parameter in the parameterized tangent line that I got in part A. But I get the same thing, so that's good. That verifies that I must have done something right. So the next thing is just the discussion questions. So I'll let you take a look at those and see you in class.